I'm very pleased to be presenting here the status of indirect dark matter searches with the ANTARES and KM3NeT neutrino telescopes. We heard a lot this morning about the need for complementarity and triangulation between different search methods. So we are here again in indirect searches. It means we look directly into sources in astrophysical environment, meaning to measure the standard model products of dark matter candidates annihilating or decaying. So these searches do unavoidably contain large uncertainties, which are mostly due to the astrophysical parametrization. Right, so messengers from astrophysical environments means typically neutrinos, photons, protons. So neutrinos, with respect to photons, they do reduce the problem of source confusion for very luminous regions, such as the Galactic Center. They're very difficult to detect. However, they need no dedicated data sets, so no pointing, no time allocation. So I'm showing here, I'm talking today about the Mediterranean telescopes, so ANTARES and KM3NeT, just to remind you that in standard data acquisition for neutrinos, detectors located in the north have access to the southern hemisphere. This was just explained by Nadesh in the previous talk. So in the standard data acquisition modus, good events for neutrinos telescopes are those coming from all the way across the Earth. So in the northern hemisphere, we need to instrument, we need in general to instrument a very large volume of a transparent medium. In the northern hemisphere, we have only water available. So water with respect to ice, it has noise, both from radioactive potassium decays and from natural luminescence in the sea. However, larger scattering length, so allowing for a slightly better angular resolution, and is of course maintainable, but also slowly moving. So this is the ANTARES neutrino detector, which is a sort of a Highlander detector. So it's going to 2021. Its shutdown point is being postponed. It has been taking data smoothly, successfully for more than 13 years of operation. And this detector consists of 12 detection lines equipped with more than 800 photomultiplier tubes, which are anchored to the sea bottom down to a depth of 2.5 kilometers. It's located about 40 kilometers offshore Toulon, the coast of France. So the legacy of ANTARES will be picked up by the KM3NeT infrastructure, which is a modular set of subdetectors with a very broad physics program. It consists of ORCA, which is a smaller, denser unit aiming at doing oscillation and mass ordering physics with very high statistics. And then two large, very high volume sparser blocks, ARCA, which are aiming to do astrophysics and multi-messenger neutrino astronomy with excellent pointing resolution. So not knowing any prior about the dark matter candidate mass, both subdetectors are in principle suitable to pick up dark matter searches. So this is our most favorable source. It's the Galactic Center, which has the largest dark matter density, and it's in very good view for ANTARES because from the Mediterranean location, so it's in the southern hemisphere. So I remind you again that what we measure is a number of events we find in a detector, and then we are converting those back into a measurement or limit on the flux, which turns into a thermally average annihilation cross-section decay rate in the source. So those are our current up-to-date released standard results with ANTARES shown here as solid lines for 5 different annihilation channels. ANTARES data of 11 years is compatible with background, so those are upper limit obtained. Those are here shown alongside with the dotted lines, which are the sensitivity in reach for a very first installation phase of the KM3NeT ARCA, so the high energy unit, with 1 year of data taking lifetime. So the energy dependency that can be achieved is, of course, different. ARCA is performing slightly worse than ANTARES at low energies because the ARCA subblock is actually aiming to do high energy astrophysics. But then on the scale, the result is comparable. And I show here in the next slide the situation of 1 year sensitivity estimation with the full ARCA, so 2 blocks of 115 lines each, as dashed lines, again shown alongside with the current ANTARES upper limits for 5 different annihilation channels. In the plot on the right panel, I'm showing one benchmark channel, so the tau plus tau minus channel, where the solid line is the 11-year upper limit reached with ANTARES. The dashed line is the estimated sensitivity for 1 year operation of KM3NeT ARCA full detector. And then these results are more or less placed in context with results, previous results by IceCube. So I'm referring to the previous publication. And then results obtained with the gamma ray telescopes, Fermi and MAGIC and Veritas, and the 10-year campaign of S towards the Galactic Center. So good chances for KM3NeT ARCA are towards the high mass region of the dark matter candidate. So other than the Galactic Center, we have searches towards the sun, which are sensitive to the dark matter nucleon scattering cross-section and would be able to yield a very clean signal, which would lead to a direct interpretation because the astrophysics neutrino background from the sun is very well known. These searches are also not affected by halo uncertainties, and they would allow for a bias-free analysis because the source is moving, and are particularly sensitive in the low velocity region where there is easier capture. Now, I'm not spending many details here because there will be a dedicated contribution, which is a poster by our colleague Daniel Lopez Cotto in this conference, which will guide you to the analysis of the sensitivity of 5 years of ORCA simulated data, which are shown here for both spin-dependent and spin-independent WIMP nucleon cross-section as red lines for 3 different annihilation channels, and the results previously achieved with ANTARES are shown here with blue lines. So I refer you to this poster for further details on this analysis. So where to search next? ANTARES has tested as well alternative scenarios, such as heavy secluded dark matter at and above 100 TeV. In these models, which are an alternative scenarios for dark matter, so the unitarity bound on the dark matter mass can be naturally evaded due to a change in the freeze-out point. And then, moreover, the annihilation spectra of relevance that can be implemented by experiments in likelihood analysis can be reliably computed. So this opens up a new search windows to the high energies that, of course, is in a good reach for ANTARES because dark matter searches for ANTARES locate in the medium to low energy possibility. Secluded dark matter is a model where dark matter interacts with a mediator on shell that is, so therefore thermal production possible, that is then decaying into standard model particle. The energy scale for this calculation, that is why I say that the spectra can be reliably computed by a modification of the PPPC4 tables, is that the energy scale in this process is therefore determined by the mediator mass, not by the dark matter candidate mass. So the neutrino signal for ANTARES would arise then from the annihilation of dark matter pairs into a couple of mediators, then decaying into standard model particles. How does it work? The standard cosmological evolution, which is shown here, is then modified by the presence of this mediator. It means that the freeze-out point happens earlier, meaning the universe at freeze-out is smaller, and at the same amount of dark matter is later more diluted, can therefore be heavier. So in this way, the bound on the dark matter mass is overtaken. So ANTARES has inspected 9 years data, finding data consistent with the background hypothesis, and we have placed limits for 4 different annihilation channel from secluded dark matter for 3 now example mass mediator masses: a light mediator 50 GeV, an intermediate mediator at 250 GeV, and a heavier mediator at 1 TeV. Now, the limits for Antares might not be particularly constraining in the very high energy region. However, these are first-time limits that push dark matter masses up to 6 PeV in this model. So it's yet unexplored territory with neutrino telescopes. The same results are shown here in details for each annihilation channel separately. So mu, tau, B, and neutrino, alongside with the 1 sigma and 2 sigma containment belts. So I am not spending more details here, but other than going towards a very high energy, we also try to push down to the maximum exploitment of existing data, which is the case for combined analysis, which joins, for instance, the ANTARES and IceCube dataset Nadej was just mentioning in the previous talk. So we have a Galactic Center combined analysis, which is able to improve upon the single experiment limits obtained from ANTARES and IceCube, and this locates in the low energy region, so up to 1 TeV. And this is again the detail of this kind of work for the 4 different annihilation channels and the variation of halo profile, which allows also for a solid assessment of the analysis procedure. So concluding, Antares issues the 11 years limit, and the KM3NeT will be able to pick up both Sun and Galactic Center analysis, promising sensitivities, testing new scenarios as well as such as the secluded heavy dark matter, and the combination of Antares with IceCube results was recently published. Where to move next? Antares' latest data sets, so the 13 years is still blind to be released. There will be first data from KM3NeT coming soon, so 6 months of ORCA is already being taken and is ready to be analyzed. And then new analysis techniques to be refined, as well as the possible combination with more other instruments, such as gamma ray telescopes. Yeah, thanks for your attention, and thanks to the organizer for the opportunity to speak.